Hi everyone, I'm Liantsoa, PhD candidate at the University of the Western Cape, supervised by Prof. Roy Martins and Dr. Dionysis. So today I'm gonna speak about my work, which is based on H1 intensity mapping, where we use the one loop EFT power spectrum, and we use for that the HIRAX radio telescope. So, what to move? So this is actually an extension of our a previous paper, which is a cosmological constraint from the power spectrum and the bispectrum of 21 intensity maps. So we use, as I said, as I mentioned, we use HIRAX, which is a radio telescope that maps most of the southern sky from 400 megahertz to 800 megahertz, and it consists of 1024 dishes. Hence, it can cover up to 15K degrees squared, which is good for cosmology since we can probe large volume. The main idea behind intensity mapping is it's a technique that allows us to look at the total intensity instead of resolving the galaxies. So we give up counting galaxies one by one, and that allows us to probe more volume, as I mentioned, and so instead of dot of galaxy, instead of looking at the source, like one by one of galaxy, we get a large pixel, which is like a CMB map for those of you who are familiar with it. And hence, it's an integrated emission length from the galaxies. And specifically in the scope of this project, as we use the telescope, so we use the H1 intensity mapping, which comes from the spin-off flip of the neutral hydrogen. You can see on the upper panel of the figure, and hence we got a 21 centimeter at redshift 0, and so on and so forth, depending on which redshift you are looking for. Coming to the modeling, the main goal is, so I'm looking at the small scales to see the effect of the clustering. So the main goal is in the modeling is to improve the signal. So hence we add non-leading order based on the standard perturbation. Which is a key proxy of nonlinear scales, but the standard perturbation comes with some problems like the UV divergence. Hence, we use the one loop EFT power spectrum to overcome that problem, and which leads you to this Euler equation, such that this Zeldovic power spectrum is the linear power spectrum, and you add some leading, non-leading orders, which is P22, P13, and at this tree level is the same as this Zaldovic power spectrum, and those are the handful of counter terms which absorb the divergence of standard perturbation, as I mentioned, and we also add some free parameters that mimic the finger of God effect, which is the effect of infalling velocity at very small scales due to the random fluctuation. So, but also, once we get this power spectrum, which is this one, the theoretical one, the observed power spectrum take into account of the volume effect, which is also called Alcock-Pazinski effect, where we take into account those two ratio. At the fiducial at each redshift comes from Planck's 2018, and yeah, but when we look at the 21 centimeter signals, it's buried in the foreground, like 2 or 3 magnitudes. Hence, we need to do some foreground avoidance, such that first on the line of set, which is the foreground radial avoidance, and we impose a cutoff at 0.1 H per megaparsec at large scales, and also due to the response of the instrument, there is a leakage of the K parallel, which is the line of set, to the K perpendicular. Hence, we have the so-called wedge. Hence, we do the foreground wedge avoidance by imposing this relation. And as I said, the wedge factor depends on the response of the telescope. Here you can see the beam taking into account all of these effects and modeling. Hence, we come to the technique that we use to constrain the cosmological parameters. First, due to the foreground cut and foreground avoidance on the radial and the wedge, such that we impose the cut, and the last equation depending on the instrument. We only have this non-shaded region, which such that this is these are the available modes for our survey given the large volume. Hence, we need a very, very larger volume to get more improvement. And coming into the methodologies that we use to do the forecast, we use the Fisher formalism, which is the Hessian of the likelihood, hence of the power spectrum, which is in terms of computing, is in the Bayesian formalism, which is equivalent of this, such that it's involved the derivatives of the observed power spectrum, and here we have the variance of the signal, such that we include the noise, which consists of the short noise, as my colleague mentioned before, short noise and the thermal noise. But in the case for intensity mapping, the the short noise is there, but very small compared to the thermal noise sense. We can neglect it, and this can be purely the thermal noise that we can compute based on the specification of the telescope that you use, whether you use single dish or interferometer mode. But in my case, I'm using the interferometer mode since it's good to study the small scales, the nonlinear scales. And as a result, the EFT give some give a reasonable constraint well at the price of the given free parameters, nuisance parameters, counter term that we've mentioned. It still gives us a reasonable constraint, and it also helps to break degeneracies in some parameters, not all. And also, we noticed that the error on the density of cold dark matter is reduced. And when adding the EFT with the Planck, the CMB information from Planck, we can get a TET constraint, which is good. And for the conclusion, I will leave you with my conclusion here, and the ongoing work noise that I'm adding at the bispectrum to which is the Fourier transform of the 3-point correlation, which helps again to get more tighter constraint, so good for us, and we are also about to submit soon a paper about the work that I've been talking. So thanks for your attention.